Great. So this actually, you don't have this slide, but you probably recognize these. I don't know if you put them on your pillow or not. But this is like how a low mass star lives, and this is how a high mass star lives. So we're talking here about stellar graveyard, okay, just to kind of emphasize, I like it when we already kind of talked about this stuff. We are talking about basically these options over here. Okay, and what those are, we said that this is a white dwarf. Love the little white dwarfs. And this we said, and actually I think you probably answered it on your test, this after a supernova, this will either be a neutron star or a black hole. Okay. Neutron star or black hole. I'll just put BH for black hole. Okay, so that we're kind of talking about the end of I almost said people's lives, the end of stars' lives. Okay, so, but we call a white dwarf a retired star, but here in a minute I'm going to talk about nova, not the TV show, but the event, the nova event, about a white dwarf, and also how a white dwarf can blow up even after it's retired. Special conditions, but it can happen. So this is the dog star, Sirius. Seriously, it's a very bright star. It's like negative 1.2 or something. And it's part of Canis Major, the constellation. It's the star called Sirius. And Sirius has a companion star. And this makes sense because actually we said that most stars up there have a companion. And we said that that's actually, when we look at their dance, we can get a fix on their mass. So this is neat. We look at the pair of stars. Sirius B is actually a retired star, and its companion, Sirius A, is still a main sequence star. Let's see if it'll... Okay, that was the visible light. Now, this is the same field of view, the same pair of objects. One is a retired white dwarf, and the other is a main sequence star. But we're looking at it at a different wavelength. Isn't that cool? Our eyes wouldn't see this. But if we switch and look at it in ultraviolet and X-rays, which if you compare ultraviolet and X-rays, those are more energetic energies. But this is kind of the information we can get looking at different wavelengths. So like we continue to hear, white dwarfs are white dwarfs are pretty compact. Why? Because the gravity's been beaten down on them. They're retired. There's no more nuclear fusion going on in their cores, white dwarfs. Okay, but what stops any more contraction basically is the thing that stops matter here from going through each other. It's the regular structure of an atom, and electrons won't pass through other electrons. So it's the regular structure of an atom with protons and neutrons in the center and electrons buzzing around. Okay, so this actually is a slide from last unit, kind of talking about, we said the whole giant stage, okay, and if it's a low mass star, meaning less than 8 solar masses, it's going to ultimately kind of lose a shell of its star material and creating this pretty planetary nebula for a while, and then it's going to cool down and become a white dwarf. Okay, so white dwarfs, though, we're going to see they have a maximum size. But, this white dwarf next to the Earth looks like, hey, how different could the white dwarf be from the Earth? But if you read the caption, it's like a similar volume, but it's the mass of our sun. So take the mass of our sun and cram it down into the size of the Earth, and you've got the density, basically, of a white dwarf. Another thing about white dwarfs, if you compare these cute little white dwarfs, these cute little retired stars, a little counterintuitive. It's funny how there's stuff in science that kind of goes against your intuition. The more massive the white dwarf, the smaller it is. And that's just because it's got more gravity to kind of squeeze it down. Okay, so we have a 1.0 times the mass of our sun, and this is 1.3 times the mass of our sun. All right. But, and sometimes this makes it to my test in some form or another. Let me change my colors. Okay. There is a very important white dwarf mass limit. And it's called the Chandrasekhar limit. And I'm probably totally butchering that, I know, Indian name. Chandrasekhar limit. But the thing is if a retired star, if a white dwarf is more than 1.4 times the mass of our sun, then basically the whole electrons kind of keeping other atoms away by other electrons, what we call electron degeneracy, it doesn't hold up anymore. Okay? So 1.4 solar masses is the biggest a white dwarf can be. I think of like Snow White and the Seven Dwarfs, the White Dwarf. Okay. So I told you that sometimes, and I'm not sure if this is really an altered slide or not. You can tell me. If it's altered, it's going to be like the photos. Like here's the first photo. That looks the same. So a star that's retired can come out of retirement, not just if its grandkids need it, but it can come out of retirement if it has a companion. Specifically, if it has a companion that is going to dump stuff on it, then a white dwarf can come out of retirement. So that's the situation we're going to be looking at. So here's the deal, and I think actually the last 2 slides of the previous chapter, we talked about kind of this situation where one star can dump on another. And we talked about how stars, as they end their lives, you know, the main sequence, they'll be giants. And so it's possible for a bloated giant to dump some of its stuff on its companion. And it's possible for its companion to be a white dwarf. That's it. Well, what happens then is one of 2 things can possibly happen. I think I'll go ahead and write them on the slide, because both of these things I'm going to tell you about the white dwarf. Both of these things can possibly happen. You can either get, and I'll explain what they are, you can either get a nova event, okay, from getting dumped on, or you can get a supernova. You're like, wait a minute, we talked about supernova. We talked about like massive stars ending their lives and blowing up. Well, there's 2 types of supernova. And actually, this type of supernova is what we call, and I'm going to explain it here in a minute, Roman numeral 1A. So actually, there's 2 types of supernova. And they both have this situation going on. So, here we go again. The thing in the center right there is your white dwarf, right? And it's funny how, I mean, stars don't care about hours and days and years. They care about, you know, hundreds of thousands of years, millions of years, that sort of thing. So here is actually some material coming off, and because they're close enough, the material actually becomes under the gravitational influence of the white dwarf, and this thing is called an accretion disk. And there's a lot of this going on, and it's very similar to if you're taking a bath or whatever, let water out of your bathtub, you pull the drain, and there at the end, you kind of have little stuff getting ready to, that's called an accretion disk. Okay, kind of spiraling in. All right, accretion disk. So, one of the things, even before a nova or a supernova type 1A event, is in that accretion disk, it goes faster and faster and faster and faster, and basically the matter is kind of tumbling on each other. The thing heats up. Okay, so actually we're going to see this kind of scenario with a couple of other, this idea of accretion disk kind of heating up. So that whole heating up can eventually, believe it or not, get hot enough to begin nuclear fusion, just in the accretion disk. Is that crazy or not? Or what? Because up to now we said the only places that you can get nuclear fusion is in the core of a star. Okay, but here it's hot enough and dense enough to begin nuclear fusion. And you figure, if this is the bloated companion, probably what is on its outer edges to be dumped on its white dwarf is going to be hydrogen. So it's hydrogen fusion. So there you go. That is a nova event. See the title? Nova. So the cool thing about nova, and can you see this scenario where, to me, okay, so it gets hotter and hotter and hotter, it gets hot enough to go ahead and begin nuclear fusion. It's like, okay, the accretion disk is gone, but the white dwarf remains. And the bloated star is still bloated, so guess what? It's more, does it again. All right, okay, so what I'm describing is kind of a repeating sort of deal. These nova can repeat themselves.
So it gets bigger and bigger?
I don't know if the white dwarf, you mean the white dwarf gets bigger? I think for a little bit, it kind of increases its mass because the material in its accretion disk increases. But to me, and I don't know, it seems like it maybe blows off the material, but it seems like it would get bigger too. But the thing is, and actually this might be, it can't get too big. Because if it gets, remember the Schneider-Secker limit, the 1.4 solar masses, if the retired star gets more mass than that, then it's screwed. Yeah, or something's going to happen. Something probably not good if you're a white dwarf. Okay, so nova event can reoccur, and this kind of, it's not as energetic as I understand as like a supernova, okay, but it's a brightening. Okay, they're pretty cool. Cool enough to name a show after them. Okay, so I'm going to put both of them side by side. So yes, you would think they could come up with a different term. Okay. Supernova. Supernova. It just means blow up. And actually, when you talk to kind of somebody on the street, if they were to do one of those little interviews of, what do you think a supernova is? Somebody would say like a star blowing up. And they'd be kind of right either way. But when we talked about a star that's more massive than 8 solar masses ending its life because it has iron in its core and it can't do, that actually is a type 2 supernova. All right, type 1a. Type 1a supernova is like I just said, where you basically have a pair of stars. One is a retired white dwarf and the other one's a bloated companion. And the bloated companion is dumping on the retired star. But it doesn't go nova, okay? It doesn't do the, okay? Instead, you can see what happens. Basically, carbon fusion. That means basically, how do I say this? White dwarfs, do you remember white dwarfs basically in their core is carbon? White dwarfs are mostly carbon. I think of it that way, kind of with the outer edges being probably helium and then hydrogen. So when carbon fusion, I'm going to go ahead and say in its core, in the core of the star begins, okay, the whole retired star blows up. The whole retired star blows up. Poor thing. Well, I can't believe I don't have more slides about that, because that's pretty dramatic. I had several slides about a nova. Nova can reoccur. Same situation is set up with a supernova type 1a. They cannot reoccur. Okay. So I have a few slides to kind of compare and contrast. The two types of supernova, okay, the one we talked about in the previous unit where a massive star blows up because it has a core with iron. Okay, that's type 2. And the one with a white dwarf getting dumped on by its companion, and it begins explosively core fusion. Well, this is a subtle thing if you ask me. Well, all this is doing is saying over time, so time is along the x-axis, Brightness is along the y-axis, and it's simply saying over time it gets dimmer and dimmer. That's all it's saying. And to me, I couldn't kind of tell the little humps there. But the light decay, the dimness over time is different between the two. This one compares and contrasts the nova that can reoccur and the supernova type 1A that occurs with a white dwarf in a binary situation with a bloated giant. One thing about it is the supernova is much brighter. Supernova are much brighter than nova. Okay. And I talked about the whole reoccurring thing. Nova can reoccur. Supernova type 1A, although they're kind of the same situation with a white dwarf, that they cannot reoccur. And the last one actually is kind of a comparison between a 1A, a supernova type 1A, and a supernova type 2. If this thing's exploding, it's a white dwarf exploding because it got dumped on too much, there's not going to be your, like you told me on the test, your neutron star, your black hole. Okay. Nothing. Nada. Okay, so to kind of summarize what's going to be different between these two sorts of supernova, type 2, massive star ends its life. Type 1A, white dwarf blows up because it got dumped on too much. Like you saw, the light curves a minute ago are going to be different. You'll also kind of see a different signature with regard to... All right. So that is one and stellar graveyard sort of situation. Now, actually, kind of picking up where we left off in the last unit, where a massive star ends its life with a type 2 supernova event. You either get a neutron star or a black hole. So the video we watched actually is going to kind of, this is kind of what the video told us. So the thing about a neutron star is it's more dense than a white dwarf. Okay, and this talks about a different degeneracy pressure, not electron degeneracy pressure, but neutron degeneracy pressure. So, I don't know. Sometimes I'll tell students to kind of think of a trash bag at Christmas time, and you got a family full of people, or you have your room full of family, and everybody's got 10 billion presents. They're little kids maybe, and you've got like one trash bag. So you go ahead and start doing your job. Fill in the trash bag, okay? And you get it, you gotta stomp on it. You only got one, stomp on it. And you might think you're about done, and that might be a white dwarf. Nice and dense, nice and compact. Oh my gosh, there's 3 more kids that have to finish their unwrapping. So then you actually have to add more material into your bag and stomp on it, stomp on it, stomp on it, stomp on it some more. Now at some point, this is kind of switching from the density of a white dwarf to the density of a neutron star. What this slide's saying and what the video said is basically if you stomp matter too much like that, what's going to happen is the structure of your atom is going to fall apart. We talked about atoms, and you guys probably already knew a little bit about atoms before this class. You got a center and you have electrons, right? Okay. Well, what this is saying is it's like the electrons from one atom can't keep the electrons from the other atom, can't keep those 2 atoms separate. So it collapses, and what this says is, and this is proven, basically it takes P stands for proton, an electron in the atoms, and when they collapse, basically, they turn them into neutrons. You're like, dude, is that like alchemy or what? So it's not normal matter. And this is what a neutron star is. There's not per se electrons there. It's just neutron soup. Is that weird or what? And why? Because you stomp on it so much. And so that's why the guy said, if you were to take, just like a teaspoonful of matter from a neutron star it would weigh a lot. A teaspoonful of a white dwarf weighs a lot, but neutrons are even more. So it is just strange. So now, instead of electron degeneracy holding up the object, it's neutron degeneracy holding up the object. The neutron soup star. So this says then, and actually the video said this too, they're picking on Lansing. Here, probably after break, you're going to see Lansing, Michigan with a black hole over it. But this isn't a black hole. This kind of gray area is a neutron star. So how do you get a neutron star? Basically, okay. So this is kind of fun. No kidding. I'll even write it up here. The acronym LGM. And so back here, I like it when they have women in science. Okay. But Jocelyn Bell saw these. I wonder if she's with Bell Labs. But anyway, I think she might have been. But she was looking in the radio region of energies. And let's see, I think, is this right? I'm not sure what direction she was looking. But basically, she was getting a tsk, tsk, tsk. And it was faster than that. Actually, well, these are units of seconds, so maybe it was every second. Okay? Like something in the radio region of the energies. And it wasn't man-made. She ruled out all that man-made. So I started to say LGM sources. I don't think they're called that anymore. But I just think this is so funny. And she must have had a sense of humor, because that stands for little green, no kidding, little green men sources. Okay. Well, how exciting, though, because they didn't know these were out there. But you know what I'm going to say. Basically, they started, this is only the first one that they looked for, the first one that they found. So they started looking at different regions of the sky, and they could find similar pulses, okay? So like, wow, we're surrounded by the green men. Well, come to find out that, like this, and hopefully you kind of remember what the video was talking about, the lighthouse. That's what I'm kind of coming up to. Because basically we were kind of seeing a neutron star whip around. Okay. So there you go. Oops. Yeah, I want to do that. So this is that supernova remnant back in, gosh, the year 1087 or something like that. Remember near the end of the last chapter we talked about, I think this is M1, Messier object number 1. And so if this is a supernova type 2 remnant, star David's guts, they're hiding in the center, maybe not even hiding, but is the pit after a massive star ends its life. You either have to have a neutron star or a black hole. And this is a neutron star. So in there actually is this and this isn't every second, this is every 0.033 seconds. I'm going to try to.
So after a supernova explodes, that stuff just stays there in the sky?
Yeah, it stays there in the sky, and it glows for a while, and for a while it might be like a million years, I don't know. But eventually the energy will dissipate into space, the energy. But the matter itself will stay around and can be recycled. We kind of talked about so looks frozen in time, doesn't it? I've heard, and maybe this reminds me kind of a planetary nebula. It's not a planetary nebula, but the planetary nebula that we looked at the other day, do you remember there's like it looks like it's still, but it really is expanding. So I don't know if this is expanding or not. I think that's a good question. If it's still, retreating or from the center. Let's see, I'm hoping this will play. If you've ever seen like If you've ever gotten the privilege to see like an ultrasound of when somebody's pregnant, that's what this reminds me of. So let's see what you think. If it plays, come on, play for me. If it doesn't, I have a plan B. That's interesting. Mm-hmm. So the Crab Nebula is the proper name, and it's M1, like I said, and it's a supernova remnant, and it has a pulsar in the center of it. Yeah, you see my pictures up there. If you go on my blog, you'll see all my pictures. I think blogs are meant so you can have an alternate persona. I don't know. Okay, it should be here. Pulsars. Crab Nebula. I'm liking that one. Okay. This should be on the internet. Should be. I checked for Heavens Above for International Space Station. There was a pass about 6:30. It was pretty low, but you can play. Go ahead. I think we're to plan C now. It should open in QuickTime. Looking from there. It's not a very long movie either. No, it wants to use that. It's going to say. We are now to plan D, if anybody's keeping track. Last one. Open with QuickTime. The other thing about not trying to find the International Space Station pass tonight is it's cloudy. Direct. My kids would say, "Mom, you have way too much stuff open." Well, I'll see if I can find that cute little picture later. So I have some slides to kind of explain why we get these, and the guy I think hopefully did a good job on the video. Why when we see these little green men sources, why is that really a pulsar creating it? And so here's the deal. Well, a few things. Remember we talked about like when a skater brings her arms in, she goes faster, the conservation of the angular momentum, conservation of spin. So basically, as you've taken something like very large, larger than our sun, and compressed it to the size of Lansing, Michigan, okay, you've really tightened. So it's really spinning very fast, okay? And the other thing is we said, we said spinning objects can create if they have charges associated with them, they can create a magnetic field. So we have it creating a magnetic field, but the beam of energy associated with the magnetic field does not necessarily, coming out the poles, basically the magnetic field, does not necessarily coincide with the rotation. So if you're kind of all right with all of that, then basically you have jets of energy going out at, not out of the rotation poles. So it's rotating around this white stick and you have jets of energy, okay? So as it goes out, it kind of makes this cone of energy, okay? So if you guys are the Earth and this is my neutron star, here you see it, or my energy beam comes from a neutron star. Here you see it, here you don't. Here you see it, here you don't. Here you see it, here you don't. And that's the kind of lighthouse sort of thing. So it ends up being kind of a beam of energy, alternating on, off, on, off, on, off. All right. So it can't be just all things kind of fall into place with this object that's creating this kind of on-off energy being a neutron star. When scientists gauge its physical size and they can see how fast it's spinning, okay, if it was normal matter, it would just kind of like fly apart because of its rotational speed. So it's got to be a neutron star. So I think I'm not going to animate this one. I think we're okay with this. Why does it spin so fast? Because it went from being, like I said, something large to something very small. And as it's like a skater pulls her arms in and goes faster. So this object also went faster. Is this the next slide? Okay. So this is your bloated companion, and here's your retired star, white dwarf. And I said that this is actually an area that a nova can occur if it's hot enough. And this fresh hydrogen can, or if enough matter makes it to if it picks up enough matter, it can actually begin nuclear fusion in its core again, wake up, and it doesn't like to do that. So it blows up as it wakes up. Kind of another thing that can happen in that accretion disk, in addition to a nova, is this. And it has to do with kind of that friction going on in the accretion disk. There can be like little burps of, wait a minute. Okay. This is, I knew that, switching gears here. This is not the same scenario as nova. Because the caption of this slide, if I was to read it, says that this companion now is not a white dwarf, this is a neutron star. Sorry. Final answer. I said, but it looks like the same picture, doesn't it? Yeah, okay. All right. Neutron star, not a white dwarf. Again, a bloated companion.
So that's a neutron star that's the companion to that giant.
Exactly. Exactly. It's a pair, and you figure they just age differently. Okay. This guy was more massive because more massive stars age faster, and instead of a black hole, it is a white. Excuse me, not instead of a white. Instead of a black hole, it is a neutron star. So it can get fed and have an accretion disk. So there we go. So now we're looking at kind of the accretion disk face on. And so nice and hot and toasty and in the accretion disk. And so not the nova events, but they're kind of akin to nova, I think. Okay, you'll get these kind of bursts. Remember, X-rays are very energetic. Like, you have gamma rays, X-rays, ultraviolet, visible, infrared. So you can have these little bursts of energy, and that's related to kind of whipping it off up on the accretion disk. Okay, so this is an X-ray burst. At the end of this part, we're going to crank it up to the more energetic gamma ray bursts. So X-ray bursts are basically companion stars. You know, you have like a bloated star and you have a neutron star. Okay, and we have the accretion disk around the neutron star. Gives you these X-ray bursts. Okay. Well, back to your wrapping paper. Okay. So you can even have maybe, well, I guess it's the same bag. Okay, so when we stuffed it pretty much full, that was a white dwarf. We're saying, dude, we got more to push in there. We stuffed it even more, that was a neutron star. Okay. This says if you take your bag of wrapping paper and you have more wrapping paper to add to it, it's possible that your neutron soup that you have now, it's not going to be happy. If you cram, and there's a limit for that. Okay, if this bag that you're filling is more than 3 times the mass of our sun, okay, what happens is basically you punch a hole through it in that the degeneracy, the neutron degeneracy, isn't going to hold that stuff up anymore. Basically, the matter, the way I think of it, is it's going to create a black hole, a stellar black hole. The matter is going to kind of, what we say, I think, kind of fall in and on itself. Neutron degeneracy doesn't stop to collapse. It collapses to basically a point we call singularity. It's a black hole. Why? Because neutron degeneracy doesn't support it anymore. In this concept of having a core after the star blew up, the type 2 supernova, if it's more than 3 solar masses, okay, and it's almost like it blinks out because you don't see it anymore, but it's an object. Okay, it's a black hole. Talk more about that after break. Okay, so we'll pick up here, 10-minute break or so, and that's kind of where I wanted to get to. And I think I've got more videos after break.